Kia ora. Let's look at another example of what we've seen before, but just to reinforce. So it's again from a past 90938 paper. Here we've got somebody that sees a fish, but he's not actually seeing the fish in this position. So where is he actually going to see this fish? So let's start and we do the same thing as we did before. We draw a guiding line from some point in the fish to James, and that'll be a straight line. Now remember, light will not travel in straight lines because it is slower in water than in the air, so it will bend. This is just simply a guiding line to know more or less where we need to draw the rays. So once we've got the guiding line, we're not going to draw it to the um, left because it's going to go into the boat. So we need to draw a guiding line. We need to draw the first ray slightly to the right until it reaches the surface. Once it hits the surface, we know that the light is going to change speeds and it's going to bend. So now we draw in the normal at 90 degrees to the surface. And this ray between the normal and the incident ray is going to be the incident angle of incidence, and that is always going to be smaller than the refracted ray because I'm going from a more optically dense to a less optically dense medium. So you can see this angle is a lot bigger than the one over here. So now that's at James. As I say, we're doing it in the general direction of James simply because that's a very small image to get things to. And we need to repeat this because we need to have two lines converging to a point to see whether the nose of the fish is. So we do the same thing again, a little bit towards the right. Don't make it too far to the right, just a little bit to the right of the first ray. Again, draw in the normal so that your angle of incidence will definitely be smaller than your angle of refraction, and do it in the general direction of James, but make sure that these are not parallel. You can see they're not parallel, they will be converging. So when we extend both the lines backwards, because remember our brain tells us that light travels in straight lines, even though it doesn't, and the point where they converge is this point over here. So we're going to see the fish at a higher point because it's closer to James. It will look bigger. It will be upright because it's again parallel to the surface. We're just looking at from the sort of the top. So it'll be parallel, but it will be vertical, upright, and slightly enlarged. And again, it's vertical because these are dotted lines to show they are not real light. This is real light coming off and bending. The dotted lines are always drawn for the virtual lines where it's actually not real. I can wave my hands in the water here. I won't be blocking any light. Whereas if I wave my hands through here, I would be disturbing the light and the light wouldn't be able to come through. But here, I would still be able to see that virtual fish because these lines have got nothing to do actually with the fish. That's just what our brains are telling us. So hopefully that's helpful. And now after all these examples, you can very easily draw ray diagrams to show the position of a virtual image. Kia ora.